Right, so okay, I'm going to attempt to just demystify and talk about a very awkward equation setup, as awkward as the Arrhenius equation in physical chemistry. So I'd like to talk about the equation of radioactivity, nuclear decay relationship. The basic equation I'd like to start off with is half-life calculation by lambda. What is lambda? Lambda is the constant. It's a constant, and it's measured in per second. So let's not worry about it too much. Then the other equation I want you to visualize is the number of nuclei decaying as a function of time. Exponent minus lambda times the time taken. This is not half-life, by the way. This is not half-life. So let me just specify that. Not half-life. Half-life is stochastic. Half-life is randomized and stochastic in nature. Stochastic in nature. A lot of people don't know the meaning of it. I'm not here to explain that. Stochastic in nature. Randomized and stochastic in nature, right? So now I'm going to use this formula to accommodate these two in here, right? This is here, this is here. So that's that. So what I'll do now is I'll do minus effective half-life. That's effective half-life, which is a reciprocal sum of the biological and physical half-life. And then I'd put this one here. There we go. So this is what the equation would actually look like. Now the number of nuclei can be further decomposed into number of moles times Avogadro's number. So I could also do A equals minus ln2 over T half mass over atomic mass times Avogadro's number times ET. So that's what we could do. And so we started off from here, these two, and this T, which is not half-life. And the half-life is itself a randomized stochastic phenomena, where the activity is defined by the lambda constant multiplying with the total number of nuclei over time. And we could use these two formula input in here to give us this. Now this whole relationship would look something like this. In a lot of questions they give you these details, they give you the half-life and the sorry, hang on, I should have just put n Avogadro's number here, Avogadro's number. So in a lot of questions they give you the half-life and they give you the time, they give you this, and they ask you what the mass is or what the atomic mass of that particular element is if they've given you the mass. That's why this question would actually look something like this. It would look something like this, being a product of log natural, which is 0.693, half-life, mass of the element, because usually it's monatomic, and then the atomic mass, and then the Avogadro's number will be coming out from your pocket, which is 6.02 times 10 to the power 23, and then the lambda may or may not be given. You may have to calculate it first inputting this formula, this one, and then you'll have the time that's been provided to you in the question. So that's how things are. It can become quite difficult, which is why I have tried to start off from here and lead it all the way down to here. So again, this is what it looks like. There we go.